Welcome to homework.
Right, Chapter 16, Problem 66. Tartaric acid is found in many fruits, including grapes, and it's the partial reason why the dry texture to wine. So we're going to calculate the pH of the titrate ion C4H4O6 2 minus concentration, and for starting off at 2.5 molar solution. So it's asking which the acid dissociating constants are listed in table 16.3, and do we have to make any approximations or assumptions when we're doing our calculations? So the first thing to note is that we should write our equation out for here, and we have the C4H4O6. This should be H2, and that's going to be our first Ka equation. And when we do that, we should have H plus HC4H4O6 minus. And now this is going to be our first equation that we're going to use for the ice table, and it's the Ka because we only lost one hydrogen of a diprotic acid. So then we're going to be using 0.250 molar for the initial, then we have 0 for the two product starting reaction. We're going to subtract X from the initial and add it to the other two. And then for the equilibrium, we just add the two rows up. Our Ka1 value from the back of the textbook is 1 times 10 to the negative 3. So whenever we have that, we can then just use the Ka1, and we know Ka1 is equal to our product over reactant, so we have H plus times our HC4H4O6 minus all over the original acid. Now, since we have that expression, we can then plug in the numbers that we are given. So 1 times 10 to negative 3 is equal to our X squared over 0.250. All right, now since we plug that in, we can then solve for X. When we solve for X, we'll be using our solver equation in our calculator. And we get the X value to be 0.0153. Now, since we have our concentration of our H plus and our HCH4O6 minus, we can then use that to be able to find our next concentration of our final tartaric ion. So to do that, we're then going to go to the next page and write out our second equation. So we knew that our first one, we had the H2. This time we only have one H, the C4H4O6 minus, and that is going to then go to C4H4O6 2 minus plus our H plus. Now, since we have this, we can then write our ice table. We know that our initial concentration for the HC4H4O6 minus in the C4HC so we know that this is going to be 0, and then these two concentrations for H plus and our other one are going to be similar, are going to be the same, and are what we calculated in the first part, which is 0.0153. And the reason why they are the same is because they are both equal to X, and the reason why we include the hydrogen concentration here is because it's just going to be adding to our hydrogen's concentration whenever we do the next deprotonation of the acid for the second conjugate base. So we know from over here, we're going to subtract, and then we're going to add x to this side. And then for part E, we're just going to add those two rows up. And then you have x, then you have 0.0153 plus x. Now we're going to do our Ka2 equation, which is equal to your products over reactants. You have your concentration is C4H4O6 minus over times your H plus ion all over your HC4H4O6 minus. And we're just going to plug in our values. So we have x times 0.0153 plus x over 0.0153 minus x. Now we need to figure out our Ka2 value from the back of the book is equal to 4.6 times 10 to the negative fifth. Since this number is so small compared to our reaction side, we can just to our initial concentration, we can just ignore it and find what x is going to be. So x squared times 0.0153 over 0.0153. And then so therefore we get the value of x, and x is going to equal to the 4.6 times 10 to the negative fifth. And so this is going to be our CH4H4O6 minus concentration for the fact that that's what x is equal to. So C4H4O6 minus is equal to 4.6 times 10 to the negative fifth. So we answered the concentration for our tartrate ion, and now we just need to figure out what the pH is for. Our pH in this equation is going to be. And to do that, what we do is we're just going to take our H plus ion and calculate our pH. So our pH is equal to the negative log of our H plus ion. And two things to note is that we have two H plus concentrations. We have the 0.0153 from the Ka, so H plus from your Ka1 is equal to 0.0153, and then your H plus for Ka2 is equal to 0.513 plus the 4.6 times 10 to the negative fifth. So when we add those two up, we get a total value of 0.01536. And so we'll just take the the negative log of that, and the pH values are going to be very similar. And so for the pK for the first one is 1.815, and if we do for the second one, we get 1.814. So for our pH, it's going to be 1.81 pH. And then to figure out the last part of the question is, did you have to make any approximations or assumptions in your calculation? The reason why we went with 1.82. The reason why we went with the first one, for the Ka1, is that there was barely any other addition of the H plus ion whenever we dissociated the second time. And so therefore, to make the approximation or assumptions to figure out which pH was correct, we had to assume that the Ka1 made the most H ion concentrations, and that what happened in Ka2 was very insignificant compared to Ka1. It was done by 1,000 times fold difference between the two values for the H plus concentrations.